Tomorrow and Thursday, big days. So tomorrow is the coding portion of midterm 2, and on Thursday, the paper portion of midterm 2. So it's going to be just like midterm 1 in terms of what you can have. So you have a cheat sheet for the midterm coding tomorrow, but nothing on Thursday. So make sure you put some code fragments on your cheat sheet for tomorrow, because that's what's most likely to help. There was an exam review session yesterday. I'm sure that Jesse went over what you need to know, but just to re-emphasize, hashing is part of the coding portion. It's not part of the, no, I take that back. So for the coding portion, you'll be expected, I guarantee it, to implement one of the hashing algorithms for insert, find, or delete for one of the 4 that we discussed: separate chaining, linear probing, quadratic probing, or double hashing. We'll give you the hash function, so don't waste your time looking over how to do the hash functions, okay? Hash function will be provided for you. On the coding portion, you're getting 2 hours this time. Now, again, I want to emphasize, I don't expect some of you to finish. Don't worry. Last time, there was a bunch of people with a 0 on code assessor who got like 39 out of 40. Okay, so this isn't something to freak out about when you can't get it to work. Okay, coding takes a little while to get things to work. This is mostly to give you time, more time than you would have if it was on paper, to do it, to think about it, to rearrange your stuff easily using typing. If it freaks you out, don't even try to run it. Please save it, okay? But if it's going to hurt your performance, don't even compile and run it. Just try to type something in, make sure you save it, okay? And just treat it like you would a paper version. Just like I did. For testing purposes, we have to provide code like the hash function. You don't need that in order to complete the exam. Please don't waste time looking at the so-called support code that's there. And one problem is a little elaborate because we have to provide you a lot of stuff to support it, okay? Please don't look at that code. You don't need to understand it in order to get, I mean, you're free to look at it, but it's not going to, I think, help you, and it's just going to slow you down, okay? So you don't need to look at all the extra code to get it to work. Okay, just like, he was first, so I'm going to let him ask the question first. I can only look at the last thing you say. Code Assessor doesn't keep a version history, okay? So I can only look at the very last thing that you say. Yes. Yeah, so on Code Assessor, yeah, if you are just, now I do care about syntax. If you give me just pseudocode, you're not going to get anything. But I know there's a couple people that I think are kind of intimidated by working with Code Assessor. So I'm just trying to make it as unintimidating as possible. Whoops, that's definitely not what I want to show you right now. Wow. Hope you got that. That was a sneak preview. Without the worksheet telling you what the problem is, I don't think it's helpful, actually. So, okay, so let's do this one. So, okay, so there is a Save Work button, okay? So you could just type in some stuff And if you say save work, it will, I know it says exam deadline, don't worry about that, but it will save it, okay? You don't have to compile it. Now, anytime you compile it, it does save it, but absolutely. Yeah, you can compile it just to see if it compiles, okay? So you can test it if you want. You can call grade this part. It's up to you how much you want to do, but sometimes when it's not working, I've seen students change it to do incredibly convoluted things when the original code probably would have worked. And I know it because some students will comment out the original code. I'm thinking, oh, you were so close with the original code, and this new code is a piece of work that isn't getting at it. Okay. Other questions? Okay. So good luck with all of that. So the remaining hour tomorrow, you'll still be working on the lab. So if you finish early, you're not excused. Just start working on the lab, okay? Because it's still helpful to be able to get the TA's help with the lab. Okay, one issue that I was seeing with Candy Crush, a couple people actually had this issue, so just wanted to point out something that happens with the list erase iterators. So I'm going to try to, actually did not do this from, I'm doing this from memory now. So I'm going to call it list erase.cpp. So here was the goal. If you remember, one of the things that you had on Candy Crush is you might have, say, a sequence, and I'm just going to have it short like this, and you need it to delete, say, all the lemons. So you need it to delete these 3 lemons. And many of you, what you did was you found a iterator that pointed to the beginning of the list. So I'll call it begin iter, that pointed to the beginning. And actually, let's see, let's do it this way to make it clear. So 2 carets, one here, one here. And this would be like the begin iter. This would be like the end iter. And if your list was named, say, candy, then you do candy erase begin iter end iter. And this actually doesn't quite work. Anyone know why? Very good, because actually it does, while it starts with the deleting at the begin iter, it ends one before the end iter. So it would actually end here, not here. So in fact, your end iter would have to be here. So that was one mistake I found with the, okay, is that clear? Mathematicians like to write these things like this. You remember this from your math classes where the square bracket meant it was inclusive and the right parentheses meant it's not? That's, mathematicians like to write it that way. So the first one's inclusive, the second one isn't. I think this is ridiculous. This is stupid. I could rant on and on about how confusing I think this is. But it's the way it is. I don't get to change it. So that was one thing. So I suggest that when you have to delete a bunch of things that you erase in this fashion, okay? Because the other way of doing it is even more susceptible to errors. So the other way of doing it that I saw, and it works if you do it carefully, is to iterate through the elements one at a time. So beginning at the first one, iterate through until you get to grape and just delete them one at a time. And this is where it gets a lot dicier. Okay, so I'm going to use pseudocode again, but I'm going to assume it's begin iter points to the beginning. So somehow I've gotten it already at the beginning. So it maybe this is how it would be. This was one way I saw it being done. While begin iter not equal, let's see, actually we would have the candy being deleted. So I'll have string candy being deleted. So that in this case would be lemon. So you're saying while the begin iter actually is equal to candy being deleted, okay, and you might say begin iter plus plus. Now I already know there's an issue here, so don't worry about the fact I already know there's an issue. And you might say candy dot erase begin iter. Okay. So the first big issue here is when you erase begin iter doesn't point to anything anymore. So when you say begin iter plus plus, it's not guaranteed to work because begin iter is gone. It doesn't point to anything. Now it might have worked, but it might not have. And the reason it might not have is because begin iter doesn't point to anything anymore. It's deleted. Okay? So you would have had to have done a save iter. So you would have to do something before you erased it, like say save iter equals begin iter. And actually you'd probably have to say begin iter plus plus. And it starts to get confusing because if you don't know this, this might not work. Does anyone know why that might not work? This is a technical point, but I'm going to change it for a moment. Just a sec. Let me try this. Int x equals 6, y equals x plus plus. What do you think the value y is? Is it 6 or is it 7? It's 6. Because the plus, what happens with plus plus is it first returns the value of x, and then it increments it by 1. So, actually did not test this out before class, but if you try this, it's quite possible that what you get is the original value of the iterator, not the next element. So you have to be careful. You'd have to probably say begin iter plus plus, save iter equals begin iter. Now you could say candy.erase begin iter, and now you could say begin iter equals save iter. Not pretty, is it? Okay? And in fact, what's still wrong here? And now up here, I went to the next thing. I said begin iter plus plus. So this is really, all I'm trying to do is show you how complicated it gets when you try to do it one at a time. Okay? So even up here, then you would have nothing because it's already been incremented. Okay, but there's another issue, which is you forgot to check to see if it was the end of the list, because what if lemon happened to end the list? So before you even got there, what you first had to do was you had to check to see whether begin iter not equals candy.end, because if you don't make that check first, then you may just run off the end of the list. And the order is important. Okay, you want to do the check to see if you're at the end of the list at the Sentinel node before you do this check, because the Sentinel node doesn't have anything in it. So when you try to dereference a pointer to the Sentinel node, bad things could happen. So the order is important. Okay, so you got to be careful about it. Now, here is the probably clever way to do it. The erase iterator actually returns a iterator to the next element in the list. Okay, you could find that out by actually going to CPP reference is a good site. So is C++.com. This one is C++.com. And you can find the different forms of the method plus descriptions of the parameters plus a description of the return value. In this case, the return value is an iterator pointing to the element that follows the element erased. Okay, so that's kind of nice. It returns an iterator to the next element in the list. But you have to actually assign it. So you would say this, and this works. Whoops. Begin iter equals candy.erase begin iter. This looks funny. So it erases whatever is pointed to by begin iter. Then it returns an iter that points to the next element and assigns it to begin iter. That's exactly what we want. So now I'll actually write it as a while loop because it's a little easier. I can say while begin iter not equal candy dot end and begin iter equals candy being deleted. This is the simplest way to do it. Okay? If this all seems a bit complicated, it is. It's a lot easier to basically find the beginning and ending spots of the list and just call erase with the beginning and ending of the range. A lot less buggy. Okay, but I just want to show you some of the pitfalls with the erase iterator. And the big one that I was seeing was people doing stuff with the begin iter after erasing it and not reassigning it like I did here. They were assuming that begin iter could still be used even though it had been erased. Okay, and that seemed to be causing some students some problems. Okay, questions about any of this? Yes.
I was just asking your while condition statement because of double equal.
Yes, I am. Thank you. Oh my gosh, if I didn't have that, it actually assigns. It would always be true. Fortunately, most compilers now give you a warning for that. It used to be silent, and you would never understand why the true branch of your if statement always worked, because it would first assign the value to the left-hand side, and then, of course, it's true. Except when you assigned 0, and then it was false. It really, but it was the kind of thing that you could look at for 2 or 3 hours and never see that you had left off that second equal sign. So usually now compilers warn you. Thank you for catching that. Other questions? Yes, John?
Just out of curiosity, the in-class midterm, it's just everything that's after the first midterm.
So yes and no. So the yes part is you're not doing like insert things into a hash table or insert things into a vector. The no part is you need to know the running times of the different data structures we've already considered, like hash tables and vectors, which are before the midterm. And know, given a scenario, like on the sample midterm, there's 7 scenarios, which one to use. So that's why I said yes and no. You need to know the gestalt, the high-level stuff about previous data structures, but I'm not going to be testing you over their implementation details, okay? Other questions? Yes? Yes. So only, so the question was in Lab 7, only submit codeprocessor.cpp, right? I think the implicit question is don't submit codeprocessor.h like you could in Lab 6, yes. So the difference was in Lab 6, it was a new lab and we wrote the grade script so we could accommodate different .h files. In Lab 7, you're back to Dr. Planck's grade scripts that don't expect you to be modifying it. So that was what was happening. Okay. Other questions? Okay. So we finished. Hopefully you did watch the video lecture that was assigned for last Thursday. If you didn't, I'm not going over it, so you better watch it before the exam on Thursday. I will also say that for the coding portion, you are not responsible for Thursday's lecture or today's lecture. That's coding only. For the in-class portion, you are responsible for it. Hence, why it is such a good idea to watch the recorded lecture for last Thursday if you didn't already do so. Okay. So, on Thursday, we talked about stacks and queues. So we talked about stacks, which are a last in, first out data structure, meaning that that's the kind of thing when it's a long line and it's been a bad day, you wish it was a stack. Because you would be last in, and as long as someone didn't come in after you, you would be first serve. Of course, you'd be grinding your teeth if you were in that line early because you'd never get served. But a stack is what is used for stack frames, okay? So it basically looks like a stack of trays, and you always take something off the top. In contrast, queues are like what we talked about earlier with dequeues. Remember, doubly ended queues you insert at the end, remove from the front. And in the STL, the data structure for that is a dequeue, D-E-Q-U-E. So now you're seeing what is happening, how it gets implemented using pointers. Okay? So we went over that as well last time. And in fact, while Dr. Planck went over the list implementation, if you remember, I told you that in practice, doubly ended queues are implemented using very clever manipulations of vectors, but don't worry about that. It is also perfectly fine to implement a doubly ended queue as a linked data structure in the way that was shown here. So where we left off was with doubly linked lists, which is what you're going to be implementing for Lab 8. And doubly linked lists are also what the STL implements for the list data structure. So in fact, you are seeing with doubly linked lists what effectively the STL is implementing. And before we go into all the code and the like, and by the way, you're not going to see code, I'm only going to go over the basic implementation because you're going to be writing the code. That's one. Two, the book gives excellent pseudocode. Okay, so you should definitely be looking at the book for help. Now, the book's code is a little too complicated, and we'll be talking about why. So here is how we are going to be implementing our doubly linked lists. So first of all, every list node has a value, and it will have a forward link. Now, often you will see this referred to as next in the textbook, and in the textbook, I think they use previous, P-R-E-V, for the previous. but Dr. Planck uses F-link for forward link and B-link for backward link. So the forward link points to the next node in the list, and the backward link points to the previous node in the list. Pretty easy, hence doubly linked list. Now, you'll notice that the list is circular, okay? You're thinking, wait, I don't notice that the list is circular. What the heck is he talking about? Well, when we get to the end of the list, notice that there's not a null pointer. You might think that the last element in the list wouldn't point to anything because, or its F-link pointer wouldn't point to anything because there's nothing after it. But in fact, it points all the way back to the first element of the list. And similarly, the first element of the list, its backlink pointer, instead of pointing to null, it goes and points to the last element of the list. So we call it circular because if I'm going through using F-links, I go through, I go through, I go through, hey, I didn't stop, back to the beginning, I keep going, dot, 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 around and around and around like a racetrack, hence circular. The book's implementation of a doubly linked list is not circular like this, and that's why its code is also more complicated than it needs to be. Okay, I'll get to why in a moment. Now, there's an issue with a circular list. That issue is you might not know where it ends. Okay, because when you get to the last element of the list, you come around. How do you know it's the last element? Here's the last piece of the magic. Remember we talked about sentinel nodes. We said that the STL had a sentinel node. So Dr. Planck's implementation also has a sentinel node. A sentinel node is a node in the list, but it effectively is a dummy node. We call it a dummy node. It does not contain a value. So the sentinel node is effectively a dummy node. So, whoops, this isn't it. This is it. Sentinel node is a dummy node. Why it's called a dummy node, I actually can't tell you. That's just how I learned it. Dummy node that contains no value. Now that's also, it turns out, a little bit of a misnomer, but for the moment we will say it contains no value. Okay, but it is in the list. And as you can see here, it is the first element of the list. And actually the list has so chapter 21 was entitled Container Objects. So the list is actually a container object. It's like you have a container around it. And it has two data structures. One is the header information, in some sense, header information. And the other is the list itself. Okay, so there's two pieces of information, the header information for the list and the list itself. The header information contains the size, so there's 3 elements, not 4. It contains the size doesn't contain the dummy node. It contains the so-called actual number of nodes containing values, and Sentinel is a pointer to the Sentinel node. So that is the first node in the list. You see it doesn't really contain a value, it's the empty string. Okay? So we're iterating through our list, and we get to this element. And we go and take the forward link, and we come to here. And the question is, how do we know when to stop? The way we know when to stop is just like with the STL list, what did we do with the STL list? How did we know when to stop? We checked against what? The sentinel node. What was returned by .end or .rend? Okay? Same thing here is you're going to have a function that returns a pointer to a sentinel node. And your code will stop when it reaches that sentinel node. Notice there's only one sentinel node. Okay, so on the exam, if I ask you to draw a list, I actually prefer you to draw it the way we've done it in class with two sentinel nodes, one at the beginning and one at the end, not using a circular list. It's a little easier for us to grade. It's a little easier to look at. But the real implementation of a list with sentinel nodes is they're circular and they have only one sentinel node. Okay? So now let's go and any questions about this implementation, this overview of this implementation? Okay, so now let's take a look at what you're going to be expected to implement. Looks like a lot, but most of these functions aren't particularly big. Okay, so even though there's a lot of functions, many of them are one-liners. Okay, so we start with the public API, and we have a constructor that is going to, what do you think the constructor needs to do for a doubly linked list? There's one thing that it's really going to have to do because it can't be done anyplace else. What do you think an empty, given what I've told you down here, what do you think an empty D list should look like? It should have a sentinel node. Okay? And we said that the list is circular. So how do you think we make a circular empty list? Just think about it. You don't have to answer it. Just think about for a moment how you might make a circular empty list. Someone want to give it a whirl? So you have a sentinel node. You've allocated it, so its value is an empty string. You have an F link and a B link. How do you think you make this circular? And what do they point to? You're right, they're equal. Yep. So they point to themselves. So the F link and the B link both point to the sentinel node. So your constructor needs to create a sentinel node and make it circular by assigning values to the F link and the B link that are equal to the sentinel node. So the constructor has to set up this empty list. Should also initialize the size to what? 0. Very good. Remember that primitive integers don't necessarily get set to 0. Okay? Here it is. If you don't set it to 0, it's not necessarily getting set to 0. I think some of you have experienced that issue already. So the other thing the constructor has to do is it needs to allocate a sentinel node and make it circular. Okay, what do you think the destructor's got to do? Deallocate what? You're right. It's going to deallocate some memory. Let's be a little more concrete. Every node in the list. Very good. Deallocate every node in the list. There might be a trick to this. Okay? Do you think we should start by deleting the sentinel node first? Should we wipe it out first, even though it's the first node of the list? John, you're shaking your head no. The answer is correct. We don't want to wipe it out first, but I want you to understand why it's a bad idea to take out the sentinel node first. Actually, good point. If you know the size of the list, you could take out the sentinel node first. Okay, so knowing the size of the list, you could take out the sentinel node first, because then you could just count from 1 to the size of the list. If you didn't have the size of the list, now what happens if you take out the sentinel node? You don't lose so much your next, but how do you know when you get to the end? If you wipe out the sentinel node and you don't know the size, you don't know when you have reached the end of the list, okay? So just, it turns out because you have this size and if you've maintained it properly, you could wipe out the sentinel node because you could then just count how many elements you have. But it's a little dangerous to wipe out the sentinel node first. Normally it goes last. Okay? But you deallocate every node in the list. Okay, empty is pretty easy. Anyone have an idea how we know if the list is empty? The size is 0. Okay, I told you some of these functions were short. Okay, if you can't figure out how to do size by now, we may have some issues. Okay, so I'll skip over size. Should be pretty clear. Push front and push back. So push front adds to the front, push back adds to the back. Okay? Now, a couple things. Before we talk about told you what push front and push back do, we have a couple other inserts. Insert before and insert after, which are going to insert before a node and after a node. So if I do insert before, let's say I was going to say give him or, so I want, let's say I was going to say, yeah, or. So I want to put it right here. I could either say insert before 6, or I could say insert after him. Okay, so insert after would be giving him as the node, as the reference node, and insert before would give 6 as the reference node. So if you look now to insert before and insert after, this is a so-called reference node. Okay, so these two things are the reference node. You have to have a reference point, right? So in insert before, you are putting the string S before that reference node. Insert after, you're putting it after the reference node. Okay, now, little thought. You probably could easily implement insert. Let's say you have an implementation for insert before. Could you implement insert after using insert before? I'm not going to tell you how to do it, but the answer is yes. Okay? If you've implemented insert before, then, and this is a perfectly legitimate thing to do on your lab, you can call insert before from insert after if you do just one very simple thing. Okay? So I'm not going to tell you the answer, but that's a big hint. Now, guess what? If you have insert before implemented and insert after, it's pretty easy to implement push front and push back using insert after or insert before. Okay? So push front pushes to the front of the list, right? So you have a sentinel node. Here's your sentinel node. Okay? And here's your current first element. So if you wanted to do push front using insert before, what would you insert before? The first element. And if you want to use insert after, what would you insert after? Not the first element. The sentinel node. Okay, so I'll leave it up to you to figure out how you could implement push back, but you should be able to figure out how you could implement push back in terms of insert before or insert after. What I'm telling you is once you've implemented either insert before or insert after, you can pretty much implement these other three functions in terms of the one function you already have implemented. I'm also telling you, go for it, okay? Because it's pretty gnarly to get one of these functions correct, as you will find out. So once you have one of these one of these two functions working, I would highly recommend that you implement the remaining three functions in terms of by calling the one function you already got correct. Okay? But this only works because you have a sentinel node. This would not work without a sentinel node. Okay? I'll show you in a moment why it doesn't work if you're not using a sentinel node. Okay? The sentinel node makes things easy. Okay? Pop front and pop back means you remove either the first element or the last element. Pop front does not mean you return the sentinel node. It means you turn the element after the sentinel node. Okay. Begin returns a pointer to the first node in the, okay, pointer to first list node, not the sentinel node, the first list node. Okay, R begin, pointer to last list node. End and R end return the same thing, a pointer to the sentinel node. So if you want to, say, implement, let's say you want to implement push front by calling insert after the sentinel node, and you're thinking, gosh, how do I get a hold of the sentinel node? I don't know, maybe you call begin or R begin. Those will give you the sentinel node. Okay, two ways to get at the sentinel node. Okay, and then erase, it deletes that particular node. Notice there's no return value. Unlike the return value for the STL list. It's a void function. So questions about any of the functions? Okay. So let's see it in action. So here's Dr. Planck's implementation of a reverse program that's going to reverse the elements of a list. So if you say, give him 6, the output should be, that's the input, the output is supposed to be 6 him give. And for those of you who don't know the significance of give him 6, watch the first video. We used to have an iconic announcer, John Ward, who when a Tennessee Vol football player would score a touchdown, would literally yell, give him 6. So, sounded a lot better when John Ward did it. What is Kessling's call when a ball hits the end zone? Into the checkerboards. Kessling was once asked, why didn't you say give him 6, as if the answer wasn't obvious. He said, that was John Ward's iconic call. I had to come up with my own. So that's the one that he uses. Okay, so we declare a D list. So again, notice that there's kind of two data structures going on. Actually, I should have noted that. So this is kind of the D list is the container object. It contains, or the header, it contains a pointer to the Sentinel node and the size. Then the D nodes are what actually store the list nodes. They are the list nodes. Okay? So the D nodes are storing the list. The D list is like the container around the whole thing and stores the header information. Okay, so here you have a D list, and he gives you back, instead of an iterator, he's giving you back an actual pointer to the node. So in the STL, you get back an iterator. You're not allowed to actually get back pointers to the actual nodes. Here, Dr. Planck is giving you a pointer to the actual node. Okay, so when he is reading elements, he's pushing them onto the front of the list. So if he has things in the order, they come in the order give him 6, give will be first, then him, then 6 if you're pushing onto the front of the list. So your list is actually going to look like this. And this is a common shorthand for a list. So it's 6 him give. So now we are inserting, we're not inserting, we are iterating through the list and printing out the values. So the way it actually looks is 6 him give. And we have a Sentinel node. I'll just call it Sentinel. Okay, and get rid of this for a moment. This goes back here. Its back pointer goes here. So what happens when you get D, what's D point to initially? D equals L dot begin. What does D point to? It points to 6. Very good. So he prints out DS because S is the value field. Okay? Then he advances the pointer with D equals DF link, so D gets advanced to him, and he points out, he prints out him, again advances D to give, and prints out give. Now advances D, and what does D point to after when we do gives F link? What does D point to? The Sentinel node. So D now points to the Sentinel node. Okay, end returns the Sentinel node. So at this point we exit the loop. Okay. Fairly straightforward. Now, last thing to go over is how we actually are going to implement an insert operation, because that's the one operation, that and erase are the two difficult operations to implement. Okay, I'll let you figure out erase. Well, I'll go over erase at a high level. I'll go over insert after in a little bit of detail. So we're going to look at insert after. Okay, so let's say that we're inserting OR. And let's say the D node we got was, I'm just going to say the D node to make it clear that it was for him. So you're getting a pointer to this. This is really a pointer to that D node. So what we want is we want OR to go between him and 6. So we have to do a number of things, which I will write out. So the first thing should be clear is we need to allocate a list node or a D node for OR. And presumably we should assign OR to the value field, right? So next we need to insert OR into the list. So we need to insert OR before him. What I strongly advise you to do is to get a second pointer that points to the, in this case, node after him. So you want to put OR, I'm sorry, I said before. See, this is why I want to do it at 3:30 when you all are so much more awake. After, not before. Insert OR after. Okay? Let me back up and say, while I'm so much more awake. Okay. So, we want to put OR after him. My first suggestion is that you get a pointer to the node after him. Okay? I would probably call it something like, I'm so creative, next node. Okay, next node. So now you have a pointer to here. I might call it my reference node or current node. I'll call it reference node. And you probably, well, not probably, you better have a pointer. I'll call it new node. So we have 3 pointers. Reference node. So you're wondering, what does Dr. van der Zanden? This is what I'm calling reference node. Get a pointer to the node after him. I'm calling that next node. And allocate a D node for OR. I'm calling that new node. So I have 3 pointers. I have 3 pointers because there's 3 nodes that need to be updated. There are 4 pointers among these 3 nodes that need updating. Can you think of what 4? We have 2 F links and 2 B links that need to be set. So we have 4. 1, 2, 3, 4. Someone give me, it's like one of those game shows. It's easier at the beginning. One of the F-links that needs to be updated. F-link of what? Him. So that is reference node. So we need to update. So reference node Flink needs to be updated. What should it point to? The new node. I'm not going to write that down. You can, but that's one. Reference node F-link needs to be updated. What's the other F-link we need to set? New node. New node needs to point to something. What should new node point to? It should point to 6, but we can't say new node equals 6. What we say new node F-link equals next node. Okay, give me a B-link that needs to be updated. Next node B-link. What does next node's B-link need to be set to? New node, very good. And the final one, the $64,000 question. Because when I was growing up, there was a game show. $64,000 question is? Final B-link. New node, very good. New node B-link, what's it get set to? Reference node. Okay, it's very easy to do these updates if you've named the nodes. It's also very easy for the TA or me or someone reading your code to get it if they see these nodes named. If instead you don't name them and you start doing awful stuff like saying reference node F-link B-link equals new node, this double traversal is nasty. What am I doing? Can anyone figure out what the heck I'm doing with this statement? Yeah, doesn't it cause a headache? It points to, okay, so reference node is him, right? And it points to 6. So the flink points to 6. It's setting 6's B-link to point to the new node. Okay, please don't write code like this. It is, yes, it is cool. I would suggest you understand code like this because it's on the midterm.
Okay.
Just to show you, A, is to force you to think about how to traverse through multiple links, and to show you how you can mess things up easily. Okay? So there will be a problem where you are going, I will give you a huge hint. Your paper portion that covers this lecture involves going through multiple links like this to show you what a bad idea it is, and then makes you fix it using simpler stuff with named nodes. Okay, so not only is this code hard to read, but it tends to lead to bugs. Very easily can lead to bugs. Okay, so let's say, to show you how it can lead to bugs, let's say that before we did this little treat, let's say we pulled this trick. Oh, Brad's doing a pun. It's Halloween. That's right. Okay. Trick or treat. Okay, so let's say right before we did that, we had said reference node flink equals new node. So we did this first. And now we execute this statement thinking, okay, we're going to set 6's B-link to be the new node. Except what are we really now setting what are we really setting to be the B-link equal to new node? New node's B-link is actually getting set to itself. That's why code with double links like that tends to get you into trouble. It's so much better when you're dealing with complicated pointers like that to start naming, putting in temporary variables, things like your next node or new node, because it will make your code a lot easier to read and make it less buggy. Okay, questions about any of this? Notice something important. Let's say that I wanted to insert after 6, which is the end of the list. There's no big deal. What will next node be made to point to? The sentinel node. By putting a sentinel node there, we don't have to worry if we're inserting at the end of the list because the last node in the list still points to something. Okay? So we don't care with insert after whether we're inserting in the middle of the list or the last item of the list. Okay? And if we say insert after the sentinel node, that's no problem either because the sentinel node, insert after the sentinel node points to the first element of the list. So if we're trying to insert in the first element, we're trying to insert something before the first element, we can simply give insert after the sentinel node. So there's no special case here. Now, let's take a look at the textbook because while the textbook does give you good code, it also is overly complicated because it doesn't use a sentinel node. So let's take a look at the insert for a... So notice in the book they are not using a sentinel node. They have a slightly different header information. So they use head to point to the beginning of the list and tail to point to the end of the list. Now, you might legitimately say, gee whiz, why can't we use common sense terms like first and last? Because we're CS people, we need to use jargon. I mean, if we use common sense terms, anyone could do it. You've got to be confusing like lawyers. Okay? Now, I think the reason head and tail was used is it had something to do with assembly language instructions early in the, when these things were first being invented. And I can't remember for sure, but at any rate, I think it has something to do with what assembly language instructions looked like and what their names were. At any rate, we call the first item in the list the head. We call the last item in the list the tail. Get used to it because that's what everyone says. They never talk about the first element of the list. They always talk about the head of the list. The head of the list means the first element of the list. The tail of the list means the last element. First element, head is first, tail is last. Get used to it. Okay, so they have a pointer to the head and a pointer to the tail. They have the last item of the list points to null, and the first item, its previous pointer, points to null. Also, just so you know, Dr. Planck's use of F-link and B-link is slightly non-conventional nomenclature. Normally, next and previous are used as the pointers, but he uses F-link and B-link. Okay, so they use null. So null is what next points to at the end of the list. previous points to null at the beginning of the list. This creates a lot of headaches, a lot of special cases. So when we want to insert into a list, we now need to consider three cases. Are we inserting at the beginning of the list? Are we inserting at the end of the list? Are we inserting into the middle of the list? Okay, we didn't have to do this with sentinel nodes. With sentinel nodes, we just assume we're inserting into the middle of the list. So here is the code for inserting into the middle of the list. And in fact, it is pretty much, remember I put up 4 things that you need to do? Here are the 4 things. So this is where the book is good. If you need some help, it's really showing you exactly how those 4 pointers need to be set that I just went through. Okay? But there is an issue. Let's say that we are inserting into the last, after the last node. So let's say that successor, or it is taking its insert operation is taking current node. Okay, so I'm going to assume that, here we go, current node is the last node in the list. So its next points to null. Here's current node. What does successor node equal? It equals current node next. What does successor node, what's its value? We're inserting at the end of the list now. It's equal to null. Do we see a sig fault coming? Which statement is going to sig fault? The last one. We have a sig fault coming because successor node is null. So when I try to go through null, that doesn't work too well. Okay? So that kind of goes down in flames. So we have to have a special case for the last node in the list. And here it is. If current node equals list tail, then, oh, this is so horrible. List tail next. But you can't really get away from it. No, you could. This is so ugly. So it is setting. Here is, so we're creating a new node and it's going at the end of the list. So it's setting list, this code. Okay, here, sorry. Let's do it again. We're inserting a new node here. So this is current node right here. So list, here's list right here. List tail next, this is next. It's setting this next pointer now to point to new node. This is new node. So that is what this statement right here does. It makes this next pointer point to new node. Then new node previous is made to point to list tail, because that's what list tail currently points to. And finally at the end, they reset this tail pointer to point to new node. Okay, so they're taking special care to make sure that they don't go through a null pointer. And of course, this next node should have been set to null. Okay, so let's say that we want to insert for the first element in the list. So we want to insert right here. So they're giving you a current node, which is the node that you want to insert after. Okay, what do you think current node is when we want to insert as the first element in the list? This is a trick question. Very good, it's null. Because what you're trying to do with this insert after is you're trying to insert after the current node. But if you're making it the first element in the list, there's nothing to insert after. Notice that by using a sentinel node, there is something to insert after. So there's no special case. But here, there is a big, ugly special case because current node has got to be null. So they are not checking that. They're checking something else, which is they are checking to see whether the list is empty here. And if it's empty, they're going to make the head and the tail point to that first element. And they are actually not handling insertion into the front of the list. Interesting. Wow. That's incredible. Okay, so I didn't even read it carefully enough this morning. They're not even trying this function. Their insert after doesn't even insert an element. It's unable to insert an element at the beginning of the list. That's amazing. Okay. So this insert routine can't even insert an element at the beginning of the list. So bottom line is be very careful with your insert function. Specifically, you can use this code, but carefully, because we have a sentinel node which is making your life a lot easier. There's no special cases with the beginning of the list, the ending of the list, or the middle of the list. Okay? So, again, remember, midterm tomorrow, make sure you don't skip lab. Test on Thursday.